He says, no, the stuff we do without thinking, the seemingly trivial act of just existing in the physical world, that is the Everest of computational challenge.
That one sale, that one painting, generated more revenue for Christie's than, well, than many entire companies make in a year.
It's just such an abstract number, $450 million.
They were likely born from the same cloud of gas and dust about 300 million years ago and are all traveling in the same direction.
So 5 of them were a cosmic family.
Okay, so I want you to imagine something for a moment. Picture the absolute peak of computing power in the late 90s. Think Deep Blue.
The machine that beat Kasparov.
Exactly. This machine has just spent, 3 hours completely dismantling the world chess champion. It gets logic, it can do symbolic integration, it proves these insane math theorems faster than any person alive. I mean, this machine is the definition of smart.
Right, it's the pinnacle of artificial intelligence as we understood it then. We built something that could conquer what we all thought was the very height of human intellect. Abstract strategic thought.
Totally. But then, picture this. As that champion machine, wheels away from the chessboard, it completely misses a chair that's just slightly out of place, clips the corner, and the whole thing just tumbles over.
Or, to be a bit more serious, if you asked that same genius machine to sort through a box of, say, slightly bent bolts and pick them out from a pile of scrap metal, it would be a total failure.
And that right there, that profound disconnect, that's the core of what we're unpacking today. It's Moravecs Paradox.
Yeah, that moment where a machine can show genius-level skill in one area, but have the perception and motor skills of, well, a toddler at best. That's the whole thing.
So let's really dig in. This idea, which is named after the computer scientist Hans Moravec, it's so counterintuitive that it didn't just cause problems for AI researchers. It basically blew up their whole understanding of intelligence. Moravec put it best in 1988. He wrote, and I'm paraphrasing a bit, "It is comparatively easy to make computers exhibit adult-level performance on intelligence tests or playing checkers.
And difficult or impossible to give them the skills of a 1-year-old when it comes to perception and mobility." That's the line.
That's the one.
And that sentence, for anyone trained in early AI, is just an intellectual punch to the gut. I mean, for decades, the thinking was that tasks that took intense conscious effort from us, the math, the logic, those had to be the hardest for a computer.
And Moravec just flips that on its head.
He completely flips the script. He says, no, the stuff we do without thinking, the seemingly trivial act of just existing in the physical world, that is the Everest of computational challenge.
So that's our mission for this deep dive. We're going to trace this intellectual fault line. Why does this weird inverse pattern even exist? We'll look at the early history of AI, the hubris of it all.
And we have to get into the deep evolutionary biology that explains it, the whole billion years argument.
Yeah, we're looking for those aha moments about where our intelligence actually comes from and how modern AI is maybe finally starting to crack these truly hard problems.
Right. We're not just talking about what computers are bad at. We're really trying to redefine what we even mean by hard and smart. So get ready to rethink everything you thought you knew about complexity.
Because sometimes just standing up straight takes more processing power than winning at chess. Okay, so let's jump right into that core observation. Section 1, the counterintuitive challenge. The basic idea was, well, simple. The stuff that feels effortless for us.
Like seeing, moving around, judging distance.
Yeah, navigating a crowded room without bumping into people. All of that was proving to be incredibly demanding for machines computationally. But the things we find hard abstract reasoning, logic computers were cracking those relatively easily.
And this wasn't just, a theoretical problem. It was an economic disaster for a lot of early AI projects. When companies tried to build automated factories, they found that, sure, optimizing the logistics plan was the easy part.
The impossible part was getting the robot arm to just pick up a bolt it had never seen before, especially if the lighting was a little bit different.
Exactly. It just couldn't do it.
So why is that so counterintuitive for us as humans? I think it's because we mix up conscious effort with computational difficulty, right? Yeah. If I spend a whole day trying to debug some code, that feels hard.
Of course.
But if I see my friend across a busy street and instantly recognize them, that feels like nothing. It's effortless.
That's the trap. It's totally the trap. If you spend years in school learning calculus, you assume it's this incredibly complex, high-value process. But walking across a gravel path without tripping, which you learned as a toddler, you assign zero computational value to that.
For the machine, though, it's the other way around.
It's completely inverted. And that's why this realization started bubbling up from a few different leading thinkers all around the same time in the 80s.
It must have been a really humbling moment for the entire field. So who else was on this track besides Moravec?
Well, a huge voice was Alan Newell, one of the founders of AI and cognitive science. He talked about this back in 1983, and he called the old way of thinking a myth of the field.
The myth being that the so-called higher functions were the real prize.
Exactly. Newell said that early researchers were certain that automating man's higher reasoning functions, the stuff you learned at a university, that was a straightforward bit. The really hard part, he argued, was automating the basic functions we share with the rest of the animal kingdom.
Wow, with the rest of the animal kingdom. That's such a powerful way to reframe it.
Isn't it?
It immediately suggests that all our abstract logic might just be a thin layer on top of this incredibly ancient, complex operating system.
Precisely. If logic is new and simple, but perception is ancient and complex, it throws our whole hierarchy of what's valuable cognitively into question. And this connects perfectly to what another giant, Marvin Minsky, was saying around the same time.
Right, Minsky focused on the unconscious.
Yeah, he focused on the hidden complexity of it. He had this amazing quote, "In general, we're least aware of what our minds do best."
Which is such a critical insight. It explains the whole AI blind spot. We only notice a process when it fails or when it takes effort.
Think about it from an engineering standpoint. Your visual system is this massive parallel processing engine. It's seamlessly integrating millions of data points, light, color, depth, motion prediction, all in real time. If it's working perfectly, your conscious mind registers none of that calculation.
You're not aware of the work.
Right. Minsky said, "We're more aware of simple processes that don't work well than of complex ones that work flawlessly."
So if I reach for my coffee cup and my brain calculates the trajectory, the grip strength, the velocity, all perfectly, I feel nothing. It's automatic. But if I misjudge the weight and spill it, that failure is what my conscious mind registers. That's when I think, oh, this is hard.
You've got it. We judge difficulty by how much time we spend struggling. But the truly complex stuff, the perception, the millions of little calculations for movement, that's all running under the hood, silent and invisible. And the very smoothness of human perception led AI researchers to wildly underestimate how hard it would be to copy.
They were trying to reverse engineer something they didn't even realize was happening.
Exactly. They were pouring all their effort into coding symbolic logic because it could see the steps and track the failures. But sensor motor skills were this black box of effortless success. It's like valuing a calculator more than the ability to just walk across a room.
And all this convergence of ideas from Moravec, Newell, and Minsky, it all led to Steven Pinker's famous summary in his 1994 book, The Language Instinct.
Ah, yes. Pinker's summary just nailed it for the broader scientific world. He wrote that the main lesson of 35 years of AI research is that the hard problems are easy and the easy problems are hard.
It's such a perfect quotable line.
It is. It showed how dramatically the AI community had misread the map of human cognition. They confused intellectual labor, like chess, with computational necessity, like seeing.
It's just a stunning example of how a whole scientific field can get sidetracked by its own bias, defining complexity only by what feels difficult to the human ego. And that intellectual shift leads us right to the heart of the why. Why is perception so brutally difficult to code? And this is where Moravec's evolutionary explanation really takes center stage.
The answer is, really, it's just time. Moravec's whole argument was that all our skills are implemented biologically, and they've been refined over and over by natural selection. So the rule is simple. The older the skill, the more time evolution has had to optimize it.
To debug the code, basically.
Exactly. To preserve improvements, find shortcuts, and just get rid of inefficient solutions. It means our brain's architecture is like a computational history book. We're running code that's been optimized over geological time just to do basic stuff like see and keep our balance.
Right. Think about what it takes to survive in a world full of predators. You need real-time, high-stakes computation for vision and movement.
Oh, for sure. Our ancestors who had, slow, clunky processors for vision, well, they didn't stick around long enough to pass on their genes. Moravec quantified this inherited knowledge in his fantastic quote. He said, "Encoded in the large, highly evolved sensory and motor portions of the human brain is 1 billion years of experience about the nature of the world."
1 billion years of experience. That's a staggering amount of programming.
It is 1 billion years of experience about the nature of the world and how to survive in it.
And what kind of computational tasks are we talking about in that billion years?
Oh, think about something like stereoscopic vision. Your brain isn't just taking 2 pictures. It's instantly calculating depth, texture, velocity, predicting where things are going to be. It's a dedicated physics engine that's been optimized by trial and error for millions of generations.
Or even something like picking up a coffee cup.
Right. You don't consciously solve friction equations. Your sensorimotor system instantly judges the material, the weight, the surface, and applies the exact minimum force needed to lift it without crushing it or dropping it. That's an optimized algorithm we just inherit.
So what does that powerful ancient engine think of our prized abstract thought, our logic, our math?
Moravec calls it the thinnest veneer of human thought.
The thinnest veneer.
Yeah, it's a new, high-level application. It's effective, sure, but only because it's running on top of and supported by that vastly older, more powerful, unconscious sensorimotor knowledge. It's piggybacking on the infrastructure built for survival.
So my ability to do algebra isn't some freestanding superpower. It's just a new app I'm running on a massive ancient operating system that was designed for dodging tigers and finding berries.
That's a perfect way to put it. And the time scale comparison is what makes it so convincing. You have to break down the time difference.
Okay, let's do it. Let's start with the ancient, effortless skills.
Okay, so those have had millions, even up to 1 billion years of evolutionary refinement. We're talking about perception, motor skills, social intelligence.
Recognizing a face, judging someone's intentions, catching a ball.
Exactly. These are the skills that make us prodigious Olympians in the natural world. They run with incredible parallel efficiency, and they're mostly unconscious. If a skill is essential for survival, like telling a predator from a shadow, evolution makes sure it's fast, efficient, and takes up zero conscious bandwidth.
Okay, now contrast that with the new skills, the effortful ones.
These are things like math, engineering, formal games like chess, symbolic logic, scientific reasoning.
Yeah.
They're evolutionarily very new, less than 100,000 years old probably. They often rely on recent inventions like language and writing.
And these are the skills that are hard for us, for humans, because they're so new.
Yeah.
Our brains didn't evolve to do abstract symbol manipulation. We have to rely on cultural evolution school, books, rules to get good at them.
And our implementation of them is inefficient.
Yeah.
It's slow. It demands a ton of conscious effort. When you solve a math problem, you're basically hijacking old circuits. You might write it down, visualize the steps. You're leveraging that old system in a new, clunky, sequential way.
So when a computer easily solves an algebra problem, it's not showing some deep intelligence. It's just using a narrow, evolutionarily young skill that happens to be easy to formalize with rules.
It's a symbolic trick that computers are great at because they excel at that kind of sequential processing. It's nothing like the messy, real-time, parallel processing you need just to see the world.
Which brings us back to that compact rule for reverse engineering.
Right. The difficulty of reverse engineering any human skill is directly proportional to how long that skill has been evolving in animals.
So the things that seem effortless to us, because they're ancient, optimized, and unconscious, are the hardest to replicate.
The effortlessness is the dead giveaway. It's the sign of incredible, hidden computational complexity.
That completely reframes our idea of genius, then. It means the most computationally valuable intelligence we have isn't writing a symphony, it's just standing on a moving boat without falling over.
Or recognizing the subtle emotional cue that stops an argument from happening. It forces you to admit that common sense, which we usually dismiss, is actually the product of 1 billion years of successful biological computation. It is the most complex thing we've ever tried to build in AI.
This realization about complexity, it wasn't an overnight thing. It was this devastating discovery that unfolded over decades. And that takes us right into the history of AI research. We have to go back to the 60s and 70s, a time of just wild optimism.
Oh, supreme confidence. I mean, the founding fathers of AI, people like Herbert Simon, they were making predictions that seem almost funny now.
Right.
Simon, I think it was 1965, he famously predicted that machines will be capable within 20 years of doing any work a man can do. The feeling was that true artificial general intelligence, AGI, was just around the corner.
And to be fair, that optimism was fueled by some real early wins. They were cracking some tough problems with what we call symbolic AI.
They were. They built programs using formal, step-by-step rules to handle logic, algebra, and especially games like checkers and chess. The success of these early programs seemed to prove their whole approach was right.
And since those things take a lot of concentration for humans, they just assumed they had conquered the peak of cognition.
That was the fatal false assumption that crept in. The assumption was that all cognitive tasks were on a single scale of difficulty. Since logic and math were hard for people, they thought, okay, once we solve these hard problems, the easy stuff like vision and walking will just fall into place.
But the paradox showed them that was completely wrong. They had solved the problems that were easy for machines because they were neat and rule-based, not the problems needed for general intelligence.
And that failure to generalize from those early wins led straight to the AI winter in the 80s. The funding just dried up.
Why, though? Why did it fail so badly?
Because the mechanism was wrong. Symbolic AI depended on a programmer explicitly writing out every single rule, step by step, if this, then that. And that works perfectly for chess, where the rules are finite and known. But try writing the rules for recognize a cat.
Right. What does a cat look like? From the side, curled up, in the dark.
The visual input is messy. It's infinite. It's all about context. The complexity just exploded beyond what any human programmer can possibly formalize.
It's that difference between sequential and parallel processing, isn't it? Chess is sequential, one move then the next. But seeing is massively parallel. It's all happening at once.
Exactly. Trying to solve these messy, parallel problems with sequential symbolic code is like trying to hammer a square peg into a round hole. It led to the collapse of all those big expert systems in the 70s and 80s that were supposed to revolutionize medicine or geology, but just fell apart when they hit any real-world ambiguity.
And this whole mess was analyzed brilliantly by Rodney Brooks, who, like Moravec, was looking at why these symbolic AI robots were failing so miserably.
Yeah, Brooks basically pointed out that the entire field had this massive intellectual bias. He said early AI research defined intelligence as the things that highly educated male scientists found challenging.
That's a brutally honest take. So what did that definition leave out?
Almost everything required for physical survival. They cared about chess, complex math proofs, abstract stuff. They completely excluded things a 4- or 5-year-old can do without thinking. Navigating a room, telling a cup from a chair in different lighting, just basic common sense.
They wrote off the complexity of a child because it was too easy for them to do consciously.
They were so focused on the tiny, fragile chimney in the intellectual castle that they ignored the massive, complex foundation holding it up. And that foundation is made of survival, not pure logic.
So this frustration with symbolic AI led Brooks to a totally new direction in the mid-80s.
A radical new direction, which he called Nouvelle AI.
A complete break. Instead of coating the veneer, he started at the foundation.
Absolutely. Brooks decided to build intelligent machines that just left out what everyone thought was the intelligence part of AI, the central abstract brain. His motto was no cognition, just sensing and action.
And he developed a new mechanism for that, the subsumption architecture.
He did, and it was designed specifically to get around the problems of symbolic AI. The old way, all sensory data went to one big central processor, which would try to build a huge model of the world, a huge bottleneck, and then decide on one action. Brooks saw that was way too slow for real-time survival.
So what did subsumption architecture do differently?
It was layered in parallel. Instead of one big brain, he had these small, independent behaviors running at the same time. The lowest layer might just be avoid obstacles. The next layer up could be wander around. A higher layer could be explore this room.
And the higher levels could override the lower ones.
Right, they could subsume them, but they didn't need the lower levels to feed into some big central world model. The obstacle avoidance circuit could run instantly, on its own, without having to consult the machine's thought process.
So he gave primacy to the foundational real-time algorithms of perception and movement, just like Moravecs Paradox suggested he should.
Exactly. Nouvelle AI was the engineering response to the paradox. It was the acknowledgement that you have to solve the billion years of evolutionary experience, the sensing and acting first. If you can't see a chair or walk across a room, being able to play chess is computationally useless in the real world.
It fundamentally taught AI that intelligence is embodied, not just symbolic. So that shift to embodied AI and connectionist models, things that mimic neural networks, that finally started to point the way forward. But for decades, the paradox still basically held true, Replicating perception was a computational nightmare.
It was.
So let's jump forward to the 2020s. What changed? What is finally challenging the paradox today?
It's almost entirely down to one thing: brute force, raw computing power. Moore's law, the idea that computing power doubles roughly every 2 years. It finally gave us the resources we needed to tackle those ancient, massively parallel problems.
And the scale is just astonishing. You mentioned Moravec actually predicted this would happen, right?
He did. Back in the 70s, Moravec calculated that to simulate just the basic sensory processing of a human brain, you'd need a computer running at about 100 million instructions per second, or MIS/PS.
Which seemed impossible back then.
Totally impossible.
Yeah.
But by the 2020s, a standard consumer GPU runs at trillions of operations per second. And it's often optimized for exactly the kind of parallel math that neural networks need. We are hundreds of millions of times faster than we were in the 70s.
And that immense increase in raw power, that's what let us finally tackle perception.
Right.
We can now sort of brute force the billion years of experience by just feeding enormous amounts of data into these massive neural networks.
Right. We train them to learn the patterns of vision and sound instead of trying to explicitly code the rules like they did with symbolic AI.
And the big breakthroughs, like deep learning in the early 2010s with datasets like ImageNet, that showed if you have enough parallel power from GPUs and enough data, the network can basically reverse engineer those fuzzy perceptual patterns that beat symbolic AI for so long.
Exactly.
Which brings us to a really compelling modern take on all this from the machine learning researcher Andrew Ng. He came up with a highly imperfect rule of thumb in 2017 that speaks directly to the paradox today. What was it?
N suggested that almost anything a typical human can do with less than 1 second of mental thought, we can probably now, or in the near future, automate using AI.
Okay, hold on. Let's unpack that. The skills that take less than 1 second of thought, that's exactly it. That's the ancient, unconscious, optimized stuff Moravec was talking about.
It is.
Quickly classifying an image, recognizing a voice, judging if an object is close or far away.
Is the paradox dissolving or maybe inverting itself? The very skills that used to be impossible for machines because they were fast and unconscious are now the first things falling to these huge parallel AI systems.
So computers finally learned how to act like that 2-year-old. They can tell a cup from a chair effortlessly, and they did it by abandoning symbolic logic for massive pattern recognition.
Precisely. And that's why modern AI is so good at these high-speed perceptual tasks. Instant image tagging, the recognition systems in self-driving cars, voice ID, translation. But, and this is crucial, the entire paradox hasn't vanished.
What do you mean?
We've gotten really good at narrow, specific perceptual tasks. But linking all those tasks into the general, flexible common sense of a toddler, that's still the frontier.
So we've solved the individual components of the sensor-motor foundation. We can build a system that sees, or one that moves, or one that hears, but getting them to work together fluidly, that's still the hard part.
That's where we are now. The paradox is still a powerful way to understand complexity, even as we start to conquer its original examples. And it's why modern cognitive science is so focused on embodied cognition, the idea that you can't separate higher thought from the body and its interaction with the world.
You can't simulate intelligence until you can simulate the general competence that comes from a billion years of physical interaction.
Exactly. The ultimate benchmark for AI isn't chess anymore. It's the general competence it takes to walk into a strange house, open the fridge, and find a snack. That effortless, general, embodied competence. That's the real test for artificial general intelligence.
And that still feels a long way off.
It does. Because that competence relies on these deep internal models for setting goals and predicting things, which are part of that same unconscious processing. We can recognize objects, but we still struggle to replicate the intuitive ability to set the right goals, or guess what others are thinking, with that same effortless fluidity. Those are the deeper, ancient skills still waiting to be conquered.
We've covered a huge amount of ground today, from the early hubris of Herbert Simon to Andrew Ng's inverted rule of thumb. Let's try to recap the absolute core takeaways from this deep dive into Moravecs Paradox.
I think the central finding, the anchor for this whole discussion, is this. The difficulty of a task for a machine is inversely related to its evolutionary age in us. The skills nature spent the longest perfecting, perception, movement, common sense, are the hardest for us to reverse engineer because they're so optimized and unconscious.
And the history of AI has just been this long, humbling process of correcting that fundamental misunderstanding of where complexity really is. Early researchers mistook the slow, conscious effort of abstract thought for the peak of intelligence.
And they dangerously overlook the invisible, powerful algorithms running our everyday census.
Which force these vital shifts, like Rodney Brooks's Nouvelle AI, breaking away from that sequential logic. It was a direct, practical response to the paradox, admitting you have to build the massive foundation of sensing and acting first, before the veneer of abstract thought can even work properly.
And while Moore's law and deep learning have finally given us the brute force to start conquering those ancient perceptual skills, the fast, sub-second tasks, the paradox is still a really powerful tool for defining what true general intelligence is. We can solve specific perception problems now, but the seamless, fluid integration of them all, that common sense that's still ahead of us.
Which leaves us with a provocative final thought then, about the nature of unconscious processing. We've established that our most powerful, complex intelligence is in the stuff we don't even realize we're doing.
Right. Recognizing a voice, setting a goal based on some implicit context, navigating a crowd while predicting where people are going to move.
So if today's AI is conquering those sub-second classification tasks, but it still needs this immense explicit training and data, what does that imply about the vast, unknown computational power needed to replicate true, flexible, general intelligence? We've only just started to map that billion years of experience stored in the hardware of our brains.
The real frontier of AI isn't abstract logic anymore. It's the invisible, optimized logic of the everyday.
Something to think about the next time you instinctively duck under a low-hanging branch while carrying a heavy box. You just performed a computational feat worthy of that billion-year legacy, and it cost your conscious mind absolutely nothing.
Indeed. It's time we all started appreciating the prodigious Olympian inside all of us.